So I'm going to do a couple of examples of applications of Stokes' theorem. For our first example, let's say that we want to compute the line integral, the vector line integral, f is a vector, where f is a three-dimensional vector given by 4z minus 2x, positive 2x. And c is a curve that's the intersection of the cylinder x squared plus y squared equals 1 and the plane z equals y plus 1. So first, we're going to have to take a look at our c. I'm going to think to myself, we are going to look at the intersection. Here's my x, my y, my z. We're looking at a cylinder of radius 1. And then I'm going to intersect it with this plane z equals y plus 1. So when y equals 0, z is up here at 1. When y is negative 1, z is down at 0. And y is at positive 1, z is up at 2. So essentially, I'm slicing this cylinder, right, with this plane that goes diagonally this way. Let's think for a second. I'm going to do this two ways. So my first way is directly. It's good review. It's something that's not going to apply Stokes' theorem. So to compute a vector line integral, recall that the formula for this is going to be given by, I'm going to erase some pieces. It's going to be given by f of c of t dotted with c prime of t dt. So our first task ahead of us is to be able to parameterize this piece right here. So let's come up with our c of t. C of t in this case is going to be a path. It goes in a circle in the xy plane, and then it has this changing height. What is our favorite parameterization of a circular path? It's going to be cosine t sine t. This gives us our circle in the xy plane, but it doesn't give us this variable height. How do we get the variable height? We have to recall the fact that it's the intersection of when z equals y plus 1. And we know what our y value is in this case. Our y value is the sine of t. So I'm going to use that to plug in here and say that that means that my z value is going to be the sine of t plus 1. So this is my path. My t values are going to go in a full circle, so my t goes from 0 to 2 pi. So we have our path. Now we need each of the pieces. We need f of c of t, and we also need c prime of t. So what's f of c of t? I'm going to take each of these components as my x, y, and z coordinates and plug it into my f function. So in this case, f of c of t is going to be equal to 4 times z, which in this case is 4 sine of t plus 4. My x component is cosine of t, so I end up with negative 2 cosine of t. And then for my last component, I get positive 2 cosine of t. This is my f of c of t function. And my c prime of t is just going to be the derivative of this function. The derivative of cosine is negative sine of t. Derivative of sine is cosine of t. And the derivative of sine of t again is cosine of t. And the derivative of 1 is 0. So I have my f of c of t, I have my c prime of t. To compute the vector line integral, I need to take the dot product of these two things and integrate as t goes from 0 to 2 pi. So my final setup for the integral, t is going to go from 0 to 2 pi of f of c of t, which is this long messy thing, 4 sine t plus 4, comma, negative 2 cosine t, comma, 2 cosine t, dotted with negative sine t, cosine t, cosine t, dt. Phew! So that's the setup. We have to take this dot product and compute the integral. If you don't feel like doing that, fast forward the video a little bit. But I'm going to do it. I think that it's important integration practice, and I've seen from some of your exams that integration practice is probably a good idea. Yeah, I'm going to erase all this just to give myself some more space. So rewriting this, I'm going to have my t values go from 0 to 2 pi. When I take this dot product, I multiply the first components. So that gives me -4 sine squared t plus 4, no, minus, this is a negative, minus 4 sine t. That's the first terms added together, first component functions. My second component functions, I get -2 cosine squared t. And then I get plus 2 cosine squared t dt. Hopefully I made this example so that it's not going to be nice. My -2 cosine squared t and my +2 cosine squared t are going to cancel one another, which is great. This is an easy term to integrate. This is a hard term to integrate. I'm going to factor out my -4 sine of t. I didn't realize it was going to be this messy. And rewrite it as -4 times the integral as t goes from 0 to 2 pi of sine squared t dt. I'm splitting it up into two integrals. -4 times the integral as t goes from 0 to 2 pi of sine of t dt. Because I know how to integrate this, I actually need a trig substitution. So what's another way to write sine of t squared? I can recall, maybe I don't recall, this is the same thing as 1/2 minus 1/2 cosine of 2t. So I'm going to use a trig substitution and rewrite this as 1/2 minus 1/2 cosine of 2t dt. I don't actually expect you to know this. This is something that I had to look up in a book to be able to figure out. So I apologize that it's a little bit messy, but it's nice to see, you know, those trig substitutions might come in handy someday. So once I do this trig substitution, now this is easy to integrate with respect to t. So I'm going to integrate the first term with respect to t, and I end up with, there's a -4 out front, times 1/2 t. What's the integral of cosine is sine, so I end up with minus 1/2 sine of 2t. Oh, I needed to do a u sub because this isn't just a t, this is a 2t. So if my u is equal to 2t, then my du is going to be equal to 2. So I need to have a 2 somewhere in here. I don't currently have a 2 somewhere in here, 2 dt. And so really, because this is a quick u substitution, I need to have a 2 in here. I multiply this by 2, and it means I need to multiply this by another 1/2, and I end up with 1/4. Evaluated, or I can wait. I'll wait on the evaluation, because this one's another term that's easy to integrate. Minus 4, the integral of sine of t is negative cosine t. So this whole thing is going to be evaluated from t equals 0 to 2 pi. And when I plug in 2 pi, the sine of 2 pi is 0, and the sine of 4 pi is also 0. So this term becomes 0. This term becomes 1/2 of 2 pi, which is just pi. So leaving the -4 out front, I end up with pi minus 0 plus cosine of 2 pi is 1 plus 4 minus, plugging in t equals 0, I get 0 in the first term. I get the sine of 0, which is also 0. And I get the cosine of 0, which is 1 times 4, which is 4. And look, I get a plus 4, I get a minus 4, and I get a -4 pi. And hopefully my final answer then is -4 pi. Notice that there were no new skills that we did here. Really all we did was compute the line integral. That's something that we've been doing in the past as well. So let's revisit this exact same example, only this time we're going to apply Stokes' theorem. And in general, that's typically what we're going to want to do, because Stokes' theorem sometimes can make these problems much, much easier. So again, recall we're computing the line integral. In this case, we have our 3-component vector field function, so we know we want to apply Stokes' theorem, because that's in R3. And our path is the same as it was before. It's the intersection of our cylinder and the plane. And if we recall our picture from before, the intersection of our cylinder and the plane gave us this circular region like this. And now, instead of computing it as a line integral along that path, we're going to consider this a surface. And we're going to compute this as, by Stokes' theorem, we know that this is equal to the double integral over the whole surface of the curl of f ds. Well, one of the tricky things that we need to do for this is to come up with the parameterization of the surface. Just like how we had to parameterize this curve, we're going to have to say, well, what is this surface in this case? And that's something that's going to be maybe a little bit tricky. I'm going to try to do the easiest parameterization possible. And by that, so when I say parameterize, I'm going to think of this as a magic carpet function. It has these circular boundaries, but really it's just living on this plane. So if I were to parameterize this plane, what would the parameterization of the plane be? I'm going to let u equal x. I'm going to let v equal y. And that means that my z component is just equal to y plus 1, which is equal to v plus 1. So this is my parameterization. The tricky part is the fact that these bounds are circular bounds, right? That in this case, it's not the fact that we have some rectangular boundaries. If I take a bird's eye view of this, we see that my boundaries are circular. By changing it from x's and y's into u's and v's, I could represent this by saying that my top boundary is the square root of 1 minus u squared, and my bottom boundary is 1 minus u squared, negative, thinking of this as a type 1 region. So if this is my parameterization, then it means that my boundaries in this case are going to be these funny boundaries. U is going to go from negative 1 to 1, and v is going to go from negative square root 1 minus u squared to the square root of 1 minus u squared. And we'll get to that in a second. So we parameterized s. That was the hard part. The rest of this now actually is pretty easy. There are a couple of things that we need to do though. Recall that in order to compute these surface integrals, we have to parameterize this. So I'm actually looking for the curl of f of our new parameterization. And then I have to dot that with my normal vector, dv du. What is our normal vector? Well, we have our surface given by this parameterization. So my partial with respect to u of this surface is going to be the vector 1, 0, 0. My partial with respect to v for this surface is going to be given by 0, 1, 1. Those are pretty easy. And so my normal vector, which is going to be given by the cross product, tu crossed with tv, this is something that I can almost do in my head. The first component, I'm going to write these above, and I'm taking the cross products sort of quickly in my head. I say my ith component is going to be 0 times 1 minus 0 times 1, which is 0. My jth component is going to be the negative of 1 times 1 minus 0 times 0, which is negative 1. And my kth component is going to be 1 times 1 minus 0 times 0, which is 1. I want to check that this is an upward pointing normal vector, and in this case it is. That my normal vector I know that my z component is 1, which means that it's going up in the z direction. My y component is -1, which means it's going backwards in the y direction. And so this is my normal vector, which is great. So this is great, we're almost done. We have our normal vector. Now all we need is the curl of f, and we need to evaluate that curl of f in terms of u's and v's. So, maybe I'll just leave this up and remember that it's our normal vector. What is the curl of f in this case? I'll just write in our normal vector right here, because we know what it is, and that way I won't lose it. It's 0, -1, 1. Great. So let's finally, computing the curl of f, maybe I should have done that first. The curl of f is going to be given by our gradient crossed with our f function, which is, again, the determinant of a 3x3 matrix, d dx, d dy, d dz. And our f components in this case are 4z minus 2x, 2x. So for my first component function, I see I get the partial derivative of 2x with respect to y, and the partial derivative of -2x with respect to z is both 0. For the jth component, the partial derivative of 2x with respect to x is 2, but it's negative because we're in the jth component. And the partial derivative of 4z with respect to z, maybe I should write it like this. It's the negative of 2 minus 4. And then for our final component, we see the partial derivative of -2x with respect to x is -2, and the partial derivative of 4z with respect to y is just 0. So this gives me 0, 2 minus 4 is -2. -2 is +2, 2. Phew! So notice in this case, this is sort of a special example, but it's an important special example to point out, that in this case, the curl of f just had constants in it. I don't have any x, y's, or z's in it. If I did have x, y's, or z's in it, then I would have to plug in my x's, y's, and z's in terms of my phi function, because I would need to use this as my phi function to plug in. But in this case, they're just constants. So what are these constants? These constants, it becomes the vector 0, 2, -2, and we're almost done. Let's go ahead and compute this dot product. We see that 0 times 0 is 0, plus 2 times -1 is -2, plus -2 times 1 is another -2, and that ends up being -4. dv du. This is where it's important to have the boundaries. So in this case, v is equal to the negative square root of 1 minus u squared up until 1 minus u squared. U is equal to 0 and 1, right? Because our boundaries in this case, it's the circular region that we're talking about. This is our region of integration. You can do this. I don't want to do this. This is messy. I like to think of things step by step. Because I have it written in u's of v's, now, finally, at the very end, I'm going to convert it to polar coordinates. Because now I don't have to think about what's going on. I don't need all these pieces. I can just think of this as a plain old integral. And I can say, I don't like the fact that I have these crazy square roots, so I'm going to convert it to polar coordinates. And in that case, I'm going to say that my theta is going to go from 0 to 2 pi in a full circle. And my radius in this case goes from 0 to 1, because it's just a circle. Again, with radius 1, of -4 r dr d theta. When I take this integral, what do I get? I get 1/2 times -4 times r squared, evaluated as r goes from 0 to 1, with an outer integral on the outside. When I plug in 1, I get -4 over 2, which is -2. Finishing off, we see that finally we have the integral of -2 d theta, as theta goes from 0 to 2 pi. When I integrate this with respect to theta, I get negative 2 theta, evaluated from theta equals 0 to 2 pi. Plugging in 2 pi, I get negative 4 pi. Da, 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 da. And we're done. So I realized that this was a lengthy example, but it does a good job illustrating Stokes' theorem. Either we could have taken the line integral directly by parameterizing the boundary of the surface and then computing that integral, or we could parameterize our surface S and take a double integral over that surface S, where our input function, instead of being f, the original function, it's the curl of f, and it's the curl of f evaluated at our parameterization phi. Thanks so much. That's it.